Hi friends, today we discuss about dimension related to measurement in physics and other related aspects. First we will consider what is dimension. See, suppose we are measuring a length. We can measure length in centimeter or meter. The three basic units of measurements in mechanics are mass, length and time. Capital M is used to represent mass, capital L is used to represent length and capital T is used to represent time. So, as I told you, length can be measured either in centimeter or meter. In either case, it is a length denoted by L. So, length when mathematically expressed has the dimension 1 with respect to L. That is length, no other operation, direct measurement. So, power of the term length will be 1. So, we say that length in its measurement has the power 1 with respect to the unit length, or dimension of length in measurement is 1 with respect to the basic unit of length. Okay. It can be either centimeter to the power 1 or meter to the power 1. So, if somebody asks what is dimension, it is the power to which the base unit is raised to get the unit of the particular measurement we are carrying out. I repeat, dimension of a particular measurement is the power to which the base unit has to be raised in the unit of that measurement. Okay. Thus we say length has the dimension 1 with respect to length. We will understand it better when we go to area, volume, etc. Now think about area. Area can be either centimeter square or meter square. Okay, there can be many other base units also, like a yard, etc., feet, etc., etc. We concentrated upon centimeter or meter, and in both cases it can be represented as L square. In the first case, length is centimeter or meter, and so its unit is L to the power 1 or base unit to the power 1. That's why we say it has the dimension 1 with respect to L. Now we come to area. It can be centimeter square or meter square, or we can say in general base unit L to the power 2. So dimension is 2. Now volume, centimeter cube or meter cube. In general, the base unit L to the power 3. So dimension of volume with respect to the base unit L is 3. Dimension of volume with respect to the base unit L is 3. Now we come to combination of two different base units. Speed. Speed can be either centimeter per second or meter per second. That is length to the power 1, time to the power minus 1. We can say that the speed has the dimension of 1 with respect to length and minus 1 with respect to time. Coming to momentum, which is a combination of mass, length and time, gram, centimeter, second to the power minus 1, or kilogram, meter, second to the power of minus 1, having the common form m to the power 1, mass to the power 1, length to the power 1, time to the power minus 1. So we can say that momentum has the dimensions of 1, 1 and minus 1 with respect to the base units of mass, length and time. So that is the concept of dimension in measurement of physics. Hope you understood that point. Okay. Now we will see what is dimensional formula. Actually, in our explanation in the previous point, we have already come through that dimensional formula. Suppose you are expressing momentum with respect to the base units m, l and t. We have already shown that its formula will be m to the power 1, l to the power 1, t to the power minus 1. So, what is dimension formula? It is the representation of a measurement of a physical property with respect to the base unit m, l and t in their appropriate dimensions. That is 1 with respect to m, dimension 1 with respect to m, dimension 1 with respect to l, and the dimension minus 1 with respect to t. So dimensional formula is the representation of a representation of a measurement, physical measurement with respect to the base units, where each base unit is raised to the appropriate dimensions. Okay. Now what is dimensional equation? Dimensional formula when equated to the property of measurement m to the power 1, l to the power 1, t to the power minus 1 is equal to momentum p or mv. So dimensional formula of a measurement when equated to the property that is measured, we get the dimensional equation. Okay, so dimensional formula is a partial presentation only. Only when it is converted to dimensional equation, it becomes meaningful. So dimensional formula is one, if it is considered as equation, it is only one part. And it is complete when it is presented as dimensional equation like this. So now we know what are dimensions, we know what is dimensional formula, we know, and what is dimensional equation, that also now we know. Okay. Now we have to understand what are meant by dimensional constant, dimensionless constant, dimensional variable, dimensionless variable. 4th, 5th, 6th and 7th, 5th, 6th, 7th and 8th. We already, 4, 5, 6, 7th term. The first, dimensional constant. These are the constant we come across in the study of physics, chemistry, etc., where the constant is having its own definite value as well as unit and so dimension. Whenever there is a unit, there is a dimension. For example, Planck's constant h 6.625 into 10 to the power of minus 34, when you express it as joule second unit. Other units are also there. For explanation, we consider only one, joule second. Is equal to 6.625 into 10 to the power of minus 34, joule expanded, kilogram, meter square, second to the power of minus 2 into second outside. Is equal to kilogram, meter square, second to the power of minus 1. So, this when converted to the MLT form, we have m to the power 1, L square, t to the power minus 1. So, this Planck's constant is having both a numerical part and a unit or dimensional part. So, it is called a dimensional constant. Now, dimensionless constant, unitless. See values 1, 2, 3, etc. All the numbers 1.5, 1 by 2, etc. are dimensionless constant. For example, kinetic energy is equal to half mv square, where half is not having any unit. So it is an example of dimensionless constant. We use the Heisenberg's uncertainty principle. Pi comes in several places. Oscillation, period of oscillation of a pendulum, etc. Pi comes where that is having a constant value. It is an endless value, but we round it off to 3.14. Okay, it is a constant and exponential constant E, natural logarithm base value 2.718. These are examples of dimensionless constants. Okay, now we have 6th and 7th dimensional variable and dimensionless variable. Dimensional variable, all the physical measurements like speed, force, even length, area, volume, all these are having definite values which may change from measurement to measurement. And at the same time, each type of these measurements are having their own particular unit and so particular dimensional expressions. Speed 3 or 4, that is wrote like that to show it is a variable, it is not a constant. 3 or 4 meter per second. 3 or 4, it is the numeral part, and the dimensional part L to the power 1 time to the power minus 1. Force 5 Newton, 5 or 6 Newton it can be, any Newton value, 5 Newton, 5 kilogram meter per second square. So 5 mass to the power 1, length to the power 1, time to the power minus 1, or minus 2, I'm sorry. So it is again having one numeral part and a dimensional part. So it is a dimensional variable. Now dimensionless variable, it is variable and at the same time it is not having any dimension, like specific gravity. Specific gravity, when we divide one unit by same unit, the units cancel, the dimensions cancel, and values like specific gravity, specific gravity, density with respect to water. So both are having same unit, they cancel. Specific gravity, then angle, dimensionless, then strain. Okay, all these are examples of dimensionless variables. So now we have idea regarding dimensional constant, dimensionless constant, dimensional variable and dimensionless variables. Okay, we proceed to the next section. Now 8th point, dimensional analysis. What is dimensional analysis? Before that, look at these terms. 100 centimeter and 1 meter are equal. So 100 centimeter by 1 meter gives you unity. Okay. 1 meter by 100 centimeter also will be unity. Similarly, 60 second and 1 minute are equal. So 60 second by 1 minute and 60 second and 1 minute are equal. So 60 second by 1 minute as well as 1 minute by 60 second, both will be unity. Okay. Such terms are called dimensional unit factor or unit conversion factors. What is their purpose? We use such terms when we convert. See, when we somebody asks 25 meter, how many centimeter? We say 2500 centimeter. Knowingly or unknowingly, we are applying dimensional analysis or we are using such terms. For example, look here, 25 meter. Our mind works it out like this to convert that to centimeter. 1 meter is 100 centimeter. It's a unit factor. So 25 meter, how much? This operation we perform. Numerical part, 25 into 100 by 1, 2500. Unit part, meter cancel, centimeter. So we converted 25 meter to 2500 meter by using appropriate unit conversion factor. Again, 350 centimeter. 350 centimeter we want to convert to meter. 350 centimeter into 1 meter by 100 centimeter. Numeral part 350 into 1 by 100, 3.5. Unit part centimeter cancels, meter. So by using this unit conversion factor, we convert value in one unit to value in another unit. This is called a dimensional analysis or factor label method or unit factor method. Okay, that is dimensional analysis. Okay. Now, principle of homogeneity of dimensions. Look here, principle of homogeneity of dimensions. Consider the equation E is equal to mc square. What is the unit here? Energy, kilogram, meter square, second to the power of minus 2. Here, what is the unit of m? Kilogram, mass. What is the unit of speed square? Meter per second the whole square. It also becomes kilogram meter square per second square. What is its dimension? M L to the power 2 times to the power of minus 2. Here the unit M L to the power 2 times to the power of minus 2. So if an equation is perfect, it must be dimensionally identical on both sides. Okay. That is the principle of homogeneity of dimension. One more thing. Here, not only with respect to different, apparently different values, but even the same value expressed in different units. Kilogram meter square per second square in SI system or in MK system. Gram centimeter per second square. Both are measurement of work or energy. What is the dimensional formula? M L square time to the power of minus 2. Here also M L square time to the power of minus 2. Okay, so here also homogeneity is maintained. Hope you understood that. That is meant by principle of homogeneity of measurements. Now we will study some important applications. Okay, actually one of the applications we have studied that dimension analysis. We have already studied one of its application, dimension analysis. This application is its extension. When there are more than one unit to be converted together, how we approach, what we will do. Let's see. To convert value from one set units to another set units. Suppose a particular measurement involving mass, length and time. That's the extreme. Let the value in one set of unit be N1. We know value into unit is a constant. N1 U1 is equal to N2 U2. That you have to always remember. One example, 1 into meter is equal to 100 into centimeter. When unit value increases, numeral part decreases. But their product will be a constant. N1 U1, N2 U2. We are applying that. N1, M1 to the power A, L1 to the power B, T1 to the power C is equal to. Now we change the units to another, like SI system to CG system like that. Example, N2 will be the new value, M2 to the power A, L2 to the power B, times T2 to the power C. Powers will not change due to the homogeneity. Okay. Now we want to get the value N2. So N2 is equal to cross multiply. Identical term can be raised to the same power. So N1 into M1 by M2 to the power A, L1 by L2 to the power B, T1 by T to the power C. This is the equation. This is the required equation. Okay. Application. One case we consider how to convert 1 joule to how much ergs. 1 joule, how much erg? Now we will write detail. 1 joule is equal to 1 kilogram meter square second to the power minus 2 is equal to some unknown N2. This is N1. 1 is N1. N2 gram centimeter square second to the power of minus 2. Therefore N2 isolated 1, this 1, kilogram by gram cross multiply whole to the power 1. Meter by centimeter whole to the power 2, second by second whole to the power minus 2. Now, for cancellation, convert kilogram to gram, meter to centimeter. Opposite way of conversion is also possible. You will reach at the same answer, but this is easy to operate. You convert this to gram, 100 gram by gram. 1000 gram by gram, 100 centimeter by 1 centimeter. Power here 1, here 2. This term cancel. So what? 1 into 1000 into 100 square is equal to 10 to the power of 3 into 10 to the power of 4, 10 to the power of 7. What is our conclusion? 1 joule, that is N1 when 1 N2 is 10 to the power of 7. That is 1 joule is 10 to the power 7 erg. This is the first and most important application here. Okay. Second application is to verify the dimensional correctness of a proved equation. For example, we know Planck's equation involving Planck's constant E is equal to hν, energy of a radiation with respect to its frequency. E energy, kilogram meter per second square. On the other side, we know Planck's constant has the unit joule second. Joule second, frequency per second. Okay. Then this joule expanded kilogram meter square per second square into another second and this second to the power minus 1 outside. It reduces to the same. So kilogram meter square per second square, kilogram meter square per second square. Actually, units are proved to be the same, dimensions are also proved to be the same. We know both are having the same dimensional formula. What? M to the power 1, L to the power 2, time to the power minus 2. This is meant by the verification of a proven equation. Okay. Now we proceed to the third application, to derive a relation that can be converted to an equation by introducing appropriate constant. Okay. For example, a case study. Suppose we want to determine the period of oscillation of a simple pendulum. Okay. First we have to perform certain experiments and see what all can affect its value. Let the given set of information be like this. Period of a simple pendulum T depends upon L, M, G and theta. We don't know what are their powers. It is not mentioned. So we equate like this. Time period T is equal to a proportionality constant K into L to the power A, M to the power B, G to the power C and theta to the power D. Now we convert them to dimensional forms on both sides. Time, its a dimensional formula is M to the power 0, L to the power 0, T to the power 1. On the right hand side, K, this is length. So L to the power A. This is mass, M to the power B. This is G, acceleration due to gravity, L, time to the power minus 2, whole to the power C, and theta to the power D. Now equate the dimensions of similar terms. First we equate the dimensions of, that is the powers of M on both sides. Here it is 0 only. Here if we verify B only. So 0 is equal to B. Now L terms, 0 here, 0. On the right hand side, L to the power C. So L to the power A here, L to the power C here. So A plus C. Now powers of time, power 1. On this side, minus 2C. Okay. Theta, no theta term here, dimensionless. So D 0. Okay. See, now look at these. We start with the C. 1 is equal to minus 2C. So C is minus 1 by 2. Now apply that in this. A plus C is equal to 0. Since C is minus 1 by 2, A is plus 1 by 2. So now we got C got, A got. Then B is already proven to be 0. Theta, B is also proven to be 0. So period T is equal to a constant K into L to the power plus half, M to the power 0, G to the power minus half, theta to the power 0. That is, it is independent of the mass of the pendulum as well as the angle tended. Okay, onto either side. Okay, then we can modify it as time period T is equal to K into root L, since it is having a plus half power, by G, since it is having a minus half power. So this is the equation. After some other study, we could prove that this K constant is 2 pi. So we have the final equation, T is equal to 2 pi under root L by G. That's why we said that in the utility, to derive a relation that can be modified to an equation. First we found out the relation. In the absence of this K, it is a relation only. But once you find out that value, it converted to an equation. Hope you understood that. Okay. Lastly, we see the limitations of this approach based on dimensions. Let's see one by one. One, limitations of dimensional studies. Only for power functions, not for log, exponential, etc. terms. See, we can make use of, we can study only equations having powers, not if they involve logarithm, exponential, etc. term. This method becomes a failure. You cannot apply that. That's the first case. Now, second, cannot apply for equations like s is equal to ut plus half at square or v square is equal to u square plus 2as. When the result is addition of two identical terms having same dimension, it is dimensionally correct. But you cannot prove this equation. Why? Because see, we can prove s is equal to ut or we can prove s is equal to half at square. But never this as together we have no verification possible. Okay. Same application, same is the explanation here. We can prove v square is equal to u square in certain situation, or we can prove v square is equal to 2as in certain other situation. But we cannot prove that v square is equal to u square plus 2as. That's the another limitation. Third, only MLT, only equations involving mass, length and time can be studied. If temperature is there is no formula. Okay. Now, a complete equation is not possible without knowing all factors. If we fail to take into account some factor which actually affect a measured property, the equation will not be perfect. For example, if you fail to take into account acceleration due to gravity in deciding the time period of a simple pendulum, that equation will not be perfect. That is another problem. Okay. And cannot determine dimensional constants. We have seen that. We see dimensionally we can prove that kinetic energy is mv square. Dimensionally we can prove that only. We cannot prove whether it is 2 mv square or half mv square or pi mv square, etc. Only from other set of experimentation we can prove that kinetic energy is half mv square. So we cannot find out dimensionless constants involved. Dimensionless constant we cannot determine. And lastly, this method does not furnish any distinction between scalars and vectors. Speed and velocity are treated identically. That is another problem. Hope you understood. Now we will do a set of problem based on dimensional studies in the next video. Okay.